Welcome to the Additive Manufacturing and Defense webinar hosted by the Eggler Institute of Technology. My name is Daniel Eggler and I'll be with you for the next 2 hours or so. We've got a really exciting webinar coming up over the next 2 hours where we're going to be exploring what is this really exciting field of additive manufacturing and how is that actually going to impact on the strategic decisions that defense is able to actually make. And so specifically, we're going to be looking at what are the applications that additive manufacturing has allowed to be possible within the defense space. And then we'll also have a look at the additive manufacturing technologies that are available to us at the present moment. And we'll look very briefly at the plastic processes as well as the metal processes. I've got with me as well the Institute Director, Mark Eggler, who is not on the screen right now, but is floating around in the background. And so if you do have any questions, please feel free to put them in the chat window. And Mark will be having a look and triaging those as necessary. And if there are some really interesting questions or questions that he believes I should stop to answer, then he will let me know and I'll have a look at that and we can have a bit of a chat then. It is a reasonably packed schedule. I don't think that you're going to be bored. We're going to be talking about lots of interesting things. And if you do see me look off to the right, it's just because I'm checking the chat window to make sure that everything is all good. I think I saw, yeah, okay. All right, so what do we have coming up over the next hour or so? Apologies. So yeah, as I mentioned, we'll be going through what those applications are, as well as the different types of technologies. That should take us around about an hour or so. I'll do my best to keep within the time, although I do have a bit of a tendency to get excited and wander off topic, but I will do my best to stay on target. At the end of the hour, we'll actually have a look at a live demonstration of how of a what we call a material extrusion process or Fused Deposition Modeling, or FDM. This is the most commonly known additive manufacturing process. Chances are, if you're thinking about additive manufacturing, this is what you've got inside your head. And so we'll have a look at a live demonstration of that. And while it's printing, we'll then open the session up to Q&A. I can just see, Brian, you've got a question that came through about will there be a recording of the webinar available? And yes, that there is. We will be putting up a recording of the webinar at the end of, well, we'll be putting it up at some point, and we'll be notifying all the participants when the webinar recording is available to review. Okay, so for those of you that do not know me, I do see quite a number of new names. No faces, everyone has their cameras off, but I do see a number of new names. And so that's wonderful and welcome. My name, as I said at the start, is Daniel Eggler, and I'm the Director of Education and Training at the Eggler Institute of Technology. On the next slide, I have a little bit about what we do at the Institute, but I'll just focus on myself quickly first. So my past experience before I came over to the Institute, where in my current role, I focus on the strategic offerings that we have at the Institute in terms of our professional education training within the defense sector. Before I came across, I was actually teaching at the University of New South Wales in Sydney as the mechanical manufacturing design lecturer, where I had a really big focus on hands-on practical applications. So it wasn't just about theory, it was making sure that people could actually make things, they could break things, they could test things, and so that they could actually get on board and see how they can actually make a difference, because that's what really matters with engineering. from my opinion, of course, is that we can actually bring things into reality. And that's one of the amazing things about additive manufacturing as well, is this enables us to do these types of things where we can actually implement real world solutions um, in all times of in all kinds of timelines and all kinds of locations. And that's what we'll discuss over the next hour. I also had the privilege of being involved in a lot of the hands-on design competition teams. Some of you may be familiar with the UNSW flagship solar car team, which was called SunSwift. They've made headlines over the years, most recently when they broke I think they had the fastest land speed record for a solar car from the top of Darwin in Australia all the way down to South Australia, which was very cool. There was also our Formula SAE team, Redback. Um, and this was all about having incredible young engineers pulling together designs and actually designing, manufacturing, and then racing their solutions. And it was absolutely inspiring to work with. I also have a PhD in vibroacoustics and active control. To cut a long, painful story short, it's almost like Harry Potter's invisibility cloak, but I was hiding submarines at a theoretical level. Application is still a bit of a while away. In terms of what the Institute does, we deliver contextualized defense learning across a range of different subject fields. So we're very well known for our education and training in military vehicle technology and systems engineering. But as you can see, we have a wide variety of courses as well, from firepower and protection, test and evaluation. Obviously, we're all here for manufacturing and fabrication today. But we actually, as you can see on screen, we have a very wide offering of education and training for the defense sector. And I'm absolutely happy to talk about what else we offer at the end of the session. But the big thing that we focus on is it's all contextualized and it's all very relevant. So unlike when I was at the university where we focused a little bit more on broad, generalized knowledge base, at the Institute, we're focused on contextualized um, application specific or industry specific learning so that it's more easily able to be absorbed and applied by our learners on the job. Okay, and I think that brings the quick intro about myself and what we do here at the Institute to wrap. So what I'll do now is I will get right into the additive manufacturing, which is why we're all here. Right, so I can see we're still. No, why I can only see the chat on my phone, but that's okay. That works for me. All right, so as we're going along, 15 is very manageable. So please feel free to put up questions as we go through, and I will be able to triage them as well with Mark's help. So, additive manufacturing, it's quite a new technology, relatively speaking, especially if you compare it to more established manufacturing processes like castings and forgings and so on. But it originally came about in the 80s. We start to see additive manufacturing appear, and it was initially used to create visualization models. So we could actually I don't think you can't see my mouse, can you? When I'm pointing at things. I don't think so. So it was initially used to create visualization models, particularly for the rapid prototyping. Oh, you can see it. Okay, excellent. I will head back here to use my models. Thank you very much for letting me know. So this was all part of the rapid prototyping movement, where we were able to initially, before additive manufacturing, the only thing we really had was to create physical models, typically from balsa wood, We could use routing to sometimes make this a little bit faster, but um, we looked for a better way to do things. And so initially we had what was called VPP, or VAT photopolymerization processes, um, which is more commonly known as stereolithography, which is um, resins that were fast cured using lasers to create these shapes. And this allowed us to very rapidly get feedback during the design process. So these were very much visualization models. And this allowed designers, particularly in the automotive space, to rapidly get feedback and information about models that you simply couldn't get just from looking at CAD, right? CAD is really powerful, it's really great, but you can't touch things. You can't engage with things physically. And that haptic feedback, that tactile feedback, is really, really important. As the technology improved, and my gosh, it's come a long way since we first started, we soon got all of the three F's in prototyping. Right. So we started with form, right, which is the part of the visualization process. And then as we got accuracy improvements, so the system, the additive manufacturing technologies got better and better in terms of accuracy, we could do fit, right? So instead of just having visualization models, we could now actually have more geometrically accurate models, and we could actually then integrate them in between components so there could actually be connections between them. And as material properties advanced, and in particular, we see the introduction of additive manufacturing of metal. Now, that was a really huge step, right? Initially, we only had plastics, then we were able to use metal and high grade plastics as well, or engineering plastics as well. We get function. So we have the full suite available to us for prototyping, and not just prototyping, but with function, we can have end use products as well. Right. So this has truly come from a very humble beginning of just visualizing models to all the way to end use products. And we see these end use products in the military, we see them in aerospace, we see them all over the place now. On the screen, you can see an image of a additively manufactured medical implant. And we'll talk a little bit about why the medical industry was one of the first adopters and why they are one of the most prolific users of additive manufacturing. Why are we so excited about additive manufacturing? There are so many reasons why. I've just got a couple of the main ones up top. Right, the main thing is we can accelerate the development process. Right, whereas before you would take a lot of time to manufacture prototypes, or perhaps you would um, simply omit a prototype because it was too expensive, either in terms of dollars or in terms of time. We can actually get that a lot faster. Moving away from the development process, there is opportunity for design optimization with additive manufacturing, things like consolidating number of processes. Um, we're able to do more complex shapes and geometries with additive manufacturing than you would otherwise be able to with conventional processes. And we'll talk about that a little bit more later, but we can consolidate that down. We can use less resources. Um, so if you can just see on the right there, we can see a Bugatti brake caliper. Now that was powder bed fusion titanium. And you could imagine to get these types of organic shapes is next to impossible using conventional processes. But all of these features, bar a couple of the pins, were able to be done in one build. Right? Whereas if you think about how you would do this conventionally, there are a number of steps you would have to take to allow or to facilitate the actual manufacturing itself. We can reduce down total number of parts, which is a nice optimization process, reduces complexity, reduces maintenance burden, lots and lots of possibilities. But, and that last point down the bottom is really key here. you still have to do your trade-off and risk analysis, right? At the risk of not getting too excited about this, or trying not to get you too excited about this, it's a really important part of the process when it comes to evaluating the suitability of additive manufacturing is to remember that it is a tool as part of your toolbox, right? There's always going to be best tool for the job. Additive manufacturing will be the best tool for some, but if you try and simply do additive manufacturing for every single solution you require to every problem, you are going to run into problems, right? So it has its place, but certainly my opinion is conventional machining in terms of castings and injection moldings and um, die castings and for all of those types of conventional machining processes aren't going away, right? It's always going to be the right tool for the right job. And so I just ask that you keep this in mind as we go through the presentation. Let's talk about why additive manufacturing would be the right tool for the right job. So there are a couple of different things, but these two I think are the most interesting and the most important. And the first one is degree of individuality. So what we're comparing here is we're comparing um, when should you pick additive manufacturing versus when is it better for more conventional or what we call generalized manufacturing, right? And so if we think about degree of individuality, this is when you need to have um, a uniqueness in the system or a uniqueness in the component tree to make things work. Now, if you just cast your mind to how we conventionally machine things or how we conventionally design things, a lot of the time we make design decisions to streamline manufacturing, right? We try and generalize a lot of the design features so that it's able to go down a production line, right? So this is a deliberate design decision that we make to improve the manufacturing efficiency, to reduce down the cost, and so on. But it may not necessarily be the decision that we would have liked to have made from a performance point of view. Right? And so in its totality, additive manufacturing represents an opportunity to design for ultimate performance because you do not have to make any concessions for conventional machining in general, right? That's a big statement, and we're going to unpack that. But that is the dream that additive manufacturing sells, is it sells this dream that, hey, if you want to do a particular feature, a particular geometry, you don't have to make concessions or sacrifices because we can handle that complexity. And we'll talk about that complexity in a second. But just focusing on degree of individuality, if you think about things like the medical industry, if we have medical implants, like dentures, for example, or hip implants, we know that the closer we can fit it to the patient, the better the outcome's going to be. Right? But that comes at a cost. And before additive manufacturing, it was really difficult, A, to even meet the complexity requirements of the individualization, but also from the cost point of view, to spin up hundreds or thousands of individualized parts tailored to a person is very difficult. But as you can see on this graph here, that as you get more individualization, this is more easily handled by additive manufacturing. And as we go across, this almost exclusively becomes the purvey of additive manufacturing. Right? We're able to nest lots of individualized components and then additively manufacture them in one batch. So individuality, very powerful pull factor for a additive manufacturing selection in terms of the process. Complexity is an even more interesting one, right? So what we can see here is the degree of complexity on the on the x-axis, and the cost on the y. And in general, additive manufacturing is this nice solid black line here, and we can see that the cost doesn't really change, and that makes sense, right? The per unit cost for additive manufacturing is sort of the same. There's no real opportunity for us to um, create tooling and molds and have the high volume throughput to bring down those costs. So if you have a look down with this gray line, this lower line here, conventional design, as the complexity goes up from low to medium to high, the costs for conventional design slowly go up as the complexity goes up because you need more tooling, you need more processes to actually handle that, right? There's a break-even point where the complexity is so much, the need to engage multiple tools, create bespoke fixtures, and so on becomes so demanding that you will be in the similar boat to do additive manufacturing. But this is the interesting part, right? Conventional machining hits a certain point where it's simply not possible to manufacture complexity of that level using conventional means. When you cannot do that, that's where additive manufacturing comes in. You can only achieve certain levels of complexity with additive manufacturing. So, for example, things like internal routing of cooling channels. Normally, we just gun barrel those and they're going to be in straight lines. But if you want to have peak performance, you would actually want to contour those cooling channels in very interesting um, patterns based on whatever your thermal analysis is. This is achievable with additive manufacturing. So it actually represents a capability gap. You can cross this capability gap by using additive manufacturing. So keeping those two things in mind, we have two key strategic capabilities that arise from additive manufacturing. The first one is reverse engineering, right? So reverse engineering, um, I think this is the one that most people, well, I think most people are familiar with both of these, but let's just dig into them. So reverse engineering, I think, represents a really exciting opportunity for the military, for the defense. This is when we have no documentation, or more broadly, the process of reverse engineering is where we create um, parts or componentry without the use of formal documentation or drawings or files, right? So all we have is the physical part, and we need to reproduce this part. This was very challenging before additive manufacturing, in particular scanning as well. Right? So we're able to create parts in a combination of scanning and additive manufacturing in highly effective and efficient ways. And we'll see a case study about that shortly. But being able to reverse engineer parts for the military is very important. And we'll get onto that in the next slide. And the other one is rapid part replacement. Right? We know that the ability to replace parts and to get systems back into service and operating is critical. Supply chains are a nightmare. Logistics is a nightmare. Um, it's almost guaranteed that the day you want a part and reach for it on the shelf is the day it's not going to be there. And being able to spin it up fast is really critical for the defense sector, right? If a part is not there, it's not uncommon to have anywhere from 3 months to 12 months as you wait for the part, depending on what it is and where it's going and who needs to get it to where and how it needs to get actually replaced. So we're going to explore these two key capabilities over the next couple of slides. All right, so let's talk about reverse engineering first. The reason why this becomes so important, particularly for defense, is because the military systems that we operate, whether they're ships or vehicles or planes, they have very long lives, right? The maintenance requirements of the service lifespan can be decades, right? Could be over 50 years. Um, And oftentimes, manufacturers simply remove the spare parts from active production. Sometimes the documents to reproduce the spares are no longer available. These situations are common, they happen a lot, and they cause massive issues. If you previously, before additive manufacturing, if you contacted a manufacturer and you said, "Oh, look, we need, another 2,000 runs of this particular part," um, they would often say, "Yes, we can do that for you," but it's very expensive. It's very expensive from the dollars side. They have to make the molds. They need to get someone to try and dig up the documentation. But then it's very expensive in terms of the time. It could take months and months and months for the machining of the molds to occur, for the the QA to occur, and so on. So this is a very big problem within the military space. 3D scanning has allowed for reverse engineering of part geometry. Very, very helpful. Prior to that, you would just have to take manual measurements and do your best to sort of match the geometry. But 3D scanning, whether it's contact or non-contact, has really opened up the capability in this space. Let's have a look at a case study here. So we had the FA-18s needed a replacement plug. And so this is over in the US. And so we had someone called McMichael um, who needed to get this part replaced. The plug was needed for an armament computer. So this was a critical component. If they were not able to get the replacement plug, then the system would be out of operation. They wouldn't be able to use it. This was a plug that allowed to communicate how many weapon stations were active. So the maintenance crew were based in Japan, and they contacted the OEM to ask for a replacement, but it had been out of circulation, and so the manufacturer advised a 500-day, all right, over a year, a 500-day replacement lead time, which is just insane, right? When you need things, uh, um, a year is definitely too far. So they looked at what else could they do. They were able to build up a technical package for the replacement plug. From the US, they were able to email it to the mechanics into Japan, and they were able to, working with some 3D printing companies, they were able to redesign, reverse engineer, and print it on site within 5 days. They were able to do that. They used just a polymer printer to print this replacement plug. And this is the great part, right? McMichael, who was responsible for this, called up after 5 days, which I assume would have been a long time for her, and said, "Do you need anything else?" And they responded that the aeroplane is already up in the air. Right? So we go from a situation, a nightmare situation of 500 days. And, I say that that's on the longer side, but it's not uncommon because of all of the stuff required to conventionally spin something like this up down to 5 days. Very, very quick. Right. The other one is rapid part replacement. So, um, as I've already mentioned, right, supply chains and logistics are a nightmare in general, but this becomes even worse during wartime. Right? We know that successful war operations are made and broken on your ability to maintain and keep your systems in operation when they are needed. Right? And so anything that's going to threaten that, in particular the replenishment timing and frequency, this becomes a really, really big problem. Compounding that, and I'm not a logistician, but from the logisticians I've talked to, um, planning the spare part inventory is very tricky. Um, They often tend to be large orders done right at the start of procurement, and then managing that becomes a bit of a challenge as well. If we then need to do a replenishment run from the manufacturer, low volume production runs are typically very costly. They have long lead times, as we saw in the previous section. And so what we want is we want to have a way around that, particularly as a stopgap. Perhaps it's not as good as the actual part, but if we can get that system up and running, that could be the difference between mission failure and mission success. And so what AM allows us to do is it allows us to use a paradigm which I've called repair as far forward as possible. So we know that there is only repairs themselves typically done at forward operating bases. They may have to be done further back depending on the complexity of the repair. But oftentimes the limiting factor isn't whether or not we can do it, but whether or not we have the part. And so additive manufacturing allows us to obtain these parts in as timely manner as possible. So we're able to, if we have a digital inventory, we can actually simply select the part that we would need and we could print them, provided it's within the printer's capabilities. All right. We could also combine that with reverse engineering if we didn't have that digital library available. Digital libraries are another interesting section that I don't talk about in today, in particular in terms of cyber risk, right, and cyber threat, but happy to have a chat about that in Q&A. What does that actually look like, though, repair as far forward as possible? If you are interested in this space, you may be familiar with these two companies. So we have Speed 3D. They've had some, what they've created is they've got an expeditionary manufacturing unit, which is a modularized cold spray technology process. It's a type of additive manufacturing, which we will talk about. And the beautiful thing about this is they've been modularized to fit into ISO 1C containers. So these are deployable and easily put on trucks, which makes it nice and convenient to integrate them into mission planning. These ones in particular come with two modules. They've got a manufacturing module and then they've got a post-processing module as well called the Speed 3D cell. Moving into this space as well, whereas before it was just Speed 3D, is Mark Forged, where they've got what's called the X7 Field Edition, which is a plastics and carbon fiber FDM printer. And this one here, they advertise it as being able to be parachuted in, and it can run off a car battery or a solar cell. But these are just two examples, and I imagine that the field will see more solutions appearing as we progress and as the technology matures. But it provides really exciting opportunities where you can get manufacturing capabilities a lot further outfield than you would traditionally have been able to. Any questions about this before I move to the actual technology capabilities, the processes themselves? I might just pause here for a question if there is any. I will also just say real quickly, I forgot to mention it, but the other really nice thing about reverse engineering is the ability to reconstruct enemy capability. We actually saw this in the Ukraine war when one of Russia's new MBTs was captured, and they were able to start the reverse engineering process to better determine what the capabilities of the Russian military were. So it's not used not just for bolstering our own supply chain, but you can also use it to reverse engineer and analyze enemy capability as well. So it is another very impressive capability. Thank you very much, Brian. I was waiting for the IP question. This one here is a interesting space. I'll briefly address it, and then I'll move through. And we can revisit this when we get to the Q&A section. But yes, it does. Yes, it does. So, for example, you will have supply contracts with OEMs, and they will have their own legal implications. IP is already a heavily contested space in terms of what applies where and how. So you can have IP rights to a design, but not the process to make that design, and vice versa. And then when you throw into the mix, what happens when it's wartime? Is it okay to reverse engineer it if it's for the internal organization, it's not for commercial benefit? It's a very, very contested, messy space right now. And lawsuits are being brought forwards almost monthly. So we are starting to get precedents forming. So that sort of deals with peacetime considerations. The question is what happens during wartime as well. So I won't go too much further into it. And I also want to stress that I'm not a lawyer, so please don't take what I say as legal advice. This is more just to bring a little bit of light to the topic, and to note that it is complex. And it is something that policymakers are grappling with, and manufacturers are grappling with, and users are grappling with, to try and work out what is and isn't okay in that space. No worries. Great to hear. Thank you very much, Brian. Great question. Happy to dig in a little deeper, but yeah, it is challenging for all those reasons you would think of. Okay, so we've talked about the applications and the exciting opportunities if we can actually manage this. So how can we do this? There are a couple of additive manufacturing processes that allow this to be possible. We will go through, up on the screen, you can see the 7 AM classes. These are all the different ways we can do additive manufacturing. For us purposes, the key ones we're focused on is photopolymerization, also known as stereolithography from a commercial point of view, material extrusion, usually referring to plastics, also known as fused deposition modeling or fused filament fabrication. There's lots of different commercialized names for it. In terms of the metals, we have powder bed fusion, which is a type of sintering process, and we also have direct energy deposition, which you probably may have heard of it as wire arc additive manufacturing, or WAM. That one has recently got a lot of attention because Relativity built a rocket that was 90% additively manufactured parts and got that in outside the upper atmosphere. Failed at stage 2 separation though, but that was all done using a directed energy deposition technique. Okay, so let's start moving through these processes. The first one is vat photopolymerization. So this was the first additive manufactured process to appear, and it was known as stereolithography. Okay, so you can see the breakdown of the definition here. Stereo, movement in 3 dimensions. Lithography is a process from photography where they essentially treat a surface to either retain or repel ink, and this is used to then form a picture. So these two concepts created the first additive manufacturing. Now, the interesting thing about this one, so this was patented in 1984 by Charles Hull, who's considered the father of 3D printing. And What this technique uses is it uses photopolymerization. So this is when we can expose a resin to UV and it causes it to solidify. And if we can do that in a particular pattern, layer by layer, then we get a 3D part. This is what it looks like at a conceptual level, right? So you can imagine we've got our platform, and I've got a video coming up to showcase this. So we have a platform, and we have a UV light source, and it scans a pattern, predetermined pattern from a computer program. And as that selectively hardens resin, then the platform lowers a little bit. We usually have some kind of resin distribution system, usually some kind of scraper or spreader to ensure a smooth application of new resin. And then we reharden, we run the scanner again, reharden another layer, platform drops down, and we just repeat this process until the part is formed. That's the beautiful thing about additive manufacturing. It's always very, very conceptually straightforward, but in practice it becomes a bit more challenging, right? But it's layer by layer construction, and this is what allows for that complexity, right? Is we're able to build up those layers in various geometries and configurations. So I have a quick video to show you of stereolithography. Oh, what's going on here? Sorry, my computer is just frozen for a second. Let me just see what's going on. Oh, okay. Well, while that's sorting itself out, let me just bring up the video because I know which video it needs to be.
SLA stands for stereolithography, a 3D printing process that uses a UV laser to cure liquid resin into hardened plastic. Upside down, or inverted stereolithography, is the most common SLA system. Depending on the machine, resin is either poured into a tank by a user or dispensed automatically from a cartridge. At the beginning of the print, a build platform is lowered into the resin, leaving only a thin layer of liquid in between the platform and the bottom of the tank. Galvanometers direct the UV laser through a transparent window at the bottom of the resin tank, drawing a cross-section of the 3D model and selectively hardening the material. The print is built in consecutive layers, each less than 100 microns thick. When a layer is complete, the part is peeled from the bottom of the tank, letting fresh resin flow beneath, and the platform is lowered once again. SLA allows for the use of a wide range of materials with diverse physical properties. Whether you're an engineer, product designer, sculptor, jeweler, or dentist.
Our next process, which is the material extrusion process, probably the most well-known, fused deposition modeling, where we literally extrude material out of a nozzle, easiest to visualize as well, right? So due to its accessibility, it has the largest install base, from hobbyists all the way through to industrial machinery. Machines themselves will vary from a couple of hundred US all the way through to 10,000, 20,000, 30,000 US plus, depending on the size and the material capabilities and so on. So this one here was invented by a guy called Scott Crump in 1988. And the myth goes that he was inspired by his daughter playing with a hot glue gun. And he decided to see if he could make a toy using a hot glue gun layer by layer. And this was the inspiration for him to create fused deposition modeling. And Scott went on to found Stratasys in 1989, and he had his first FDM machine in 1991. And as I'm sure almost all of you know, the Stratasys is one of the largest players in the additive manufacturing market today. The process itself, how does it work? We have a robot, typically on a gantry, that moves an extruder in two principal directions, and the platform goes up and down. As the extruder head is heated, material comes out at a constant rate. So we can see the internals of the nozzle over the head over here. On this diagram, you can see that there's two extruder heads for two materials. There's a build material and support material. One of the things about additive manufacturing, which we don't really need to think about in conventional manufacturing, is we have the use of supports, right? Because we are literally building layer by layer. If there are overhangs or islands, these must be supported by something, right? Otherwise, gravity will cause the part to fail. So we typically build support material to physically provide the support for any part that may fall down due to gravity, and these must be removed. Right, so this is a post-processing requirement for additive manufactured parts. We can use, typically we're talking about plastics when it comes to material extrusion processes, but we can do wire metal. We just need a stronger heat source. All right, so this is the material extrusion process.
The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts, including hand sanding, assembly, and cosmetic paint.
Okay, so I just wanted to quickly also point out that we can do very interesting 3D printing of carbon fiber as well. Here we have an example of a carbon fiber printed soft jaw in 2 days. Normally this would take a number of weeks to do the design and pre-preg and layup for carbon fiber. One of the really exciting things about being able to use carbon fiber and 3D printing, particularly some of the solutions on the market, is the ability to control the placement and orientation of fibers. Right, so we're actually able to dictate the layup, and this is what gives it the strength, right? There are carbon fiber printers on the market without the ability to control the orientation of the fibers. This is not going to give you the carbon fiber solution that that you were looking for from an engineering point of view. Carbon fiber and composite applications require you to be able to control placement and orientation, because that's where the strength optimization occurs. So this is able to be done in additively manufactured parts as well. So this is a very impressive capability of additive manufacturing. Just keep in mind, if you're looking into this, you need to know that you can control placement and orientation of fibers. That brings us to the end of the plastic processes. We'll now quickly go through the metal processes. So there are two primary metal processes of interest to us. On the left, we can see powder bed fusion. This is a type of sintering process where we have a powder bed and we use lasers to selectively melt them and allow them to fuse together. And we also have directed energy deposition, which is very similar from a process point of view to material extrusion, but we're now using metal powders or metal filament to create the part. And we'll see those in a second. Okay, so let's start with powder bed fusion. Here it is conceptually. We have a powder, a powder chamber in the build volume. And as what you can see here is as the build platform, we initially have a powder layer. We have a laser that will selectively melt the powder and it creates what we call a melt pool. And this creates essentially the fused metal. Once we have our layer complete, the platform lowers, we get more powder, and then the process repeats itself. So, conceptually quite similar to what we typically do with powder bed fusion. I will also point out that a lot of people, when it comes to additive manufacturing, there is a lot of concern, particularly around metal additive manufactured parts, particularly because up here. Thank you, just so I can see all of you. Particularly because of our experience with HAZ, right, or heat affected zones from welds. So we know that these form structurally, these are the areas where during test and evaluation, these are selected for special attention because these form weak points. So we are always testing the welds for the weak points. And at first blush, powder bed fusion feels like a welding process, right? It's almost like millions and millions of welds, mini welds to create a part. Where it's different, particularly for powder bed fusion, is the control of what we call the melt pool. So as the laser is melting, selectively melting the powder, it's controlling the size of that melt pool, it's controlling the temperature inside that melt pool, and as a result, it's able to control the phase of the material as it cools. Right, so this is a very key difference between welding and powder bed fusion is the ability to control the melt pool. And this is what allows it to be a very strong part, and you don't have those weaknesses that you would typically have with welding, right? There are some limitations and issues with powder bed fusion, particularly if you think about residual heat in the near vicinity of the melt pool. We often have formation of a skin. This is where partially melted powder adheres to the main part. And there are some other issues as well. I won't get into them here, but it's important to note that the key challenges with powder bed fusion is the repeatability of the process, in particular with powder management. So there needs to be a very effective strategy in terms of managing the powder, because as you are heating and reheating and cooling the surrounding powder, over time this can change the powder properties, and this can obviously then affect the build. So powder management is a very key issue when it comes to powder bed fusion. And they often use a recycling management process where they are cutting fresh powder with the current powder inside the thing, inside the actual build platform. The other thing to note about powder bed fusion is that there are big questions in terms of how to manage the efficiency, because if you can see this build platform here, you've got to fill it completely with powder. Okay, so even if you have a very small part, you still have to fill the whole thing with powder. So where possible, you want to try and match the part build to the appropriate build chamber. All right. I just want you all to appreciate that. Normally, I would spend an hour on just this process in one of our courses. So I'm just giving you a very, very high level blow by blow there. I do have another video to show you, which is of the titanium brake calipers being built. So this one was by Bugatti. All right, so the next material process is directed energy deposition. Very similar to material extrusion, but we're now able to create a melt pool. All right, so you can almost think of it like a hybrid combination between laser cladding, which is actually an additive manufacturing process before the concept of additive manufacturing existed. And so obviously laser cladding was used to provide surface applications and to improve corrosion resistance and all kinds of things well before the 80s. As well as a laser CNC, like a 5-axis laser CNC. And the really interesting thing about directed energy deposition is we can have multiple feeds. So we can either have a powder feed, a wire feed, we could have both, we could have different materials. And so what that opens up in an exciting way is you can actually control, what's the word I'm looking for? Alloying, all right? So we can actually have different material compositions as we're going through. So we can actually create all these different alloys, and we can have what's called functionally graded materials, which is as we are building the material, we can change the percentage of various alloying elements so that they have unique properties as a continuous part, rather than just having a particular material for the entire component. So very, very interesting capabilities with directed energy deposition. As you can see, very similar, but what we have is the melt pool. Right, so similar to powder bed fusion, because we're working with lasers, we can control a melt pool, and because we control the melt pool, similar to powder bed fusion, we control the phases as the material cools down, and we can also, as a result, have very interesting, unique or non-equilibrium grain structures. So we can, if you have done any metallurgy, you'll know about phase diagrams and phase transition diagrams. But the ability to control the melt pool controls the material properties. So we can have all kinds of interesting and unique material composition possibilities using directed energy deposition. Another interesting area that we see emerging is this concept of hybrid manufacturing. So this is where we integrate additive manufacturing with subtractive manufacturing on the same machine. So whereas before you might have to do additive manufacturing and then take it to a subtractive manufacturing machine for post-processing, hybrid machines do both in the one platform. And this opens up some really interesting opportunities where you're able to prepare parts, you're able to do testing, you're able to do finishing all in the one machine. You're able to remove material so you can prepare it for the next layer of additive manufacturing. So this is a really, really exciting area within the manufacturing space, this hybrid additive manufacturing. And I've just got a very interesting video to show you of this. The last process that I'd like to talk about is cold spray technology. So metal powders. So cold spray is a process that's been around for a while. It actually predates additive manufacturing. It just wasn't used for additive manufacturing, but it was an additive process, right? Where metal powders were accelerated to very high velocities, and then they do cold fusion to weld onto the material. Now, there are a number of benefits of cold spray. And so the SPE3D that I was talking about right at the start of the presentation, they use this technology. And a key benefit here is there's no heat affected zone, and it's able to work with thermally sensitive materials because there is no heat, right? There's just a little bit of heat from accelerating it to very high velocities. But other than that, there is no heat issues. Right? So it's able to build parts up. It's very useful to repair existing parts. It can apply coatings. But the thing to note about cold spray is it cannot join two separate pieces of metal. So it's not a welding process like a fusion welding process where you can join two pieces. This one here has to be just building up single pieces, single components. There are some other challenges as well. Building these up, it's very difficult to get nice defined edges. So building freestanding parts can be a little bit tricky. If you think about how powder deposits, right? If you've ever built a ridge of sand at the beach, you'll know that the powder tends to form like a hill. And so we have this part process as well with cold spray technology. So careful part planning is needed, and of course post-processing to bring that final shape into tolerance.
Cold spray is a technique that allows metal powders to be deposited to form coatings, repair parts, or additively manufacture components. Powder particles are accelerated in a supersonic gas stream. Upon impact, particles deform rapidly, oxide layers are fractured, and a metallurgical bond can be formed. Particles remain within the solid state throughout the process, with minimal heat input to the substrate. The solid-state nature of the process brings a number of benefits, including the ability to deposit oxygen-sensitive materials without shielding, such as aluminium and titanium, and create deposits with high density and bond strength, with manageable levels of residual stress or distortion. The process is well suited to repair applications and is qualified for use on a number of aerospace and defense platforms. There's also an increasing interest in additive manufacturing due to the very high deposition rates available, the ability to process challenging materials, and the potential for multi-material structures.
Last couple of things to talk about. What are the challenges to integrating AM? The biggest one by far is confidence in the part in terms of validation and qualification. Certification is not standard yet. It's done on a case-by-case basis. Certainly certification for additive manufacturing is in industry. It does exist. It's just not widespread and as easily utilized as more conventional manufacturing processes. So it undergoes a full ISO 9000X process on a case-by-case basis. But Aerospace certainly has many form, fit, and function certified parts across that sector. Security risks, we've talked a little bit about this, but IP theft is one thing, but the one I want to talk about more is compromised digital files. So when it comes to storing your digital files, a big challenge could be, well, how do you know if someone has tampered with or modified a file? Now, it's one thing to delete a file, but it's also another to sabotage it, right? Where you're able to make changes, change geometries, change structural design decisions that would compromise the integrity of the file. How would you know? How would you know? What processes would you have in place to confirm that the digital file that you are about to print or to additively manufacture has not been compromised and it is the correct one? That also goes to configuration management issues, making sure that those are working. And as you can imagine, that in itself is a whole conversation. Could be some supply chain shock. Anytime we introduce a new process, it's going to need a change in mindset in terms of where are you going to store the powders, how are you going to store the powders, how are you going to maintain the powders and filaments and so on, what are the power requirements, lots of different considerations within the supply chain, and not just in terms of the physical supply chain, but the digital supply chain as well. How does that look to make sure that you don't have any disruptions? There is going to be an initial cost, both in terms of the setup, but in terms of the investment in time to actually get that training, which is this skills gap. Right? One of the biggest feedback that I get from the defense sector when it comes to talking about additive manufacturing is that people simply choose not to consider an additively manufactured solution simply because they're not familiar with it. They're not aware of what are the possibilities and what are the limitations, so they stay with what is safe and what is known. And those are missed opportunities. Those are missed opportunities for performance, for efficiency improvements, and so on, if, of course, they are the right opportunities that were identified. So certainly as we progress to more additively manufactured solutions, we're going to need to see a increase in support and training from the design side, making sure that those that are working on the design and implementation of additive manufactured parts have been supported, as well as the operations side from the technicians, but also policymakers need to be aware of what are the capabilities and limitations and so on. It requires a whole of organization and awareness of what are the opportunities and limitations to effectively deploy additive manufacturing. Otherwise, if it's not done correctly, and this is a very common occurrence across industry, is people will pick a project, it'll be too complex, it will be inappropriate for the technology, they will have a horrific experience, and then they'll say, well, that's why additive manufacturing is not a good thing. But of course, that's not correct, right? It's simply a tool in your tool belt. You have to pick the right tool for the right job. Just quickly about what we offer in terms of supporting the professional development for those interested in additive manufacturing. The big one is we are focused on making sure that we have our courses focus on AM that's relevant to defense. So we're focusing on what matters. What do you need to know to either leverage the technology or make a decision about adopting the technology or otherwise? And so we have 1 day, 2 day, and 3 day courses. The 2 day and 3 day courses have hands-on workshops where there's an opportunity to actually print some parts, get a feel for what are the physical quirks or the manufacturing specific quirks of additive manufacturing. Remember, it's layer by layer, so you can actually do things that you haven't been able to do with conventional, and we'll see this in the demonstration. And as well as a number of other things, and it gives some really critical insight into what are the realistic considerations you're going to have if you want to put a design and get someone to actually be able to manufacture it and utilize it correctly, right? As always, it's always best to be able to get your hands on and to get those feels for those really simple life lessons that you just wouldn't get if you hadn't had a chance to actually print something yourself. Here's just a timetable of our 3-day additive manufacturing workshop. As you can see here, it is very much tailored for military. We've got military specific modules, things like reverse engineering, obsolescence management. We've got the supporting ecosystem and infrastructure, which looks at supply chain management as well. We've got additive manufacturing. The additive mindset is all about what do you need to do? What do you need to consider if you want to leverage additive manufacturing effectively? What are the difference between how we do things from a conventional point of view, whether it's casting or CNC or otherwise, versus additive? Because if you approach additive manufacturing with a conventional manufacturing mindset, you're simply not going to get the full benefit out of it. And so you can see that each day we have a large section devoted to hands-on workshops, case studies, and so on. So it's very, very, this is a very good course. We ran a 2-day version of this for the US Marine Corps earlier this year in August, and it was very well received. And certainly if you're interested, or if you'd like to for us to share some testimonials, happy to do so. In fact, there's a testimonial here from one of the USMC participants. So this was a 2-day version, and on their recommendation and feedback, this is what sparked off the 3-day version, which is a more advanced, tailored version for those working within the defense sector. All right, so now just to finish off the last 25 minutes or so, I've got a live demonstration. Let me just bring this one up so that I can show you. Just bear with me while I get everything squared away. There we go. Can everyone see the screen there?
Yes.
Excellent. So just to quickly show the software and what we're working with as well. Let me just quickly show this to you here. Oh, all right, let me just turn this one on so you can see. Oh, you can see my little test print here, but this is the system that I'm using for the demonstration. This is a Bamboo A1 Mini. This is also the system that I use when I deliver courses. So we come to you and I bring this printer along with me. So it's a nice little printer for demonstration purposes. Nice and portable. It's obviously got a very small bed. And you can see I printed something this morning just to make sure that it was working. Just a little tank. So going back to the software itself, this is a very, very quick overview of how the softwares work. By and large, they all work the same way. There's hundreds of these softwares out there. Excuse me, my voice is starting to go. The most common free one is what's called Cura, but just know that most manufacturers will have their preferred or internal software, but they all follow the same process. So I'm able to demonstrate this from a conceptual point of view. I obviously won't go through everything, but this is just a very quick overview of how these work. So you can see here, I've just brought in a part, And the reason why I like this part is it's nice to demonstrate what additive manufacturing can do, right? Because what you can see here is you've got a sphere and a cube, okay? And how would you conventionally machine this? It would be next to impossible, right? To actually get something in like this. Very, very, very challenging, if not impossible. But with additive manufacturing, nice and straightforward, nice and easy to do. So we've imported our CAD file, right? And so, you know, this is assuming all the design work's done. We're now just preparing it for additive manufacturing. And we can see up the top, we have a prepare tab, we have a preview tab, a device tab, and so on. Prepare is where we do all of the work to get the part ready for printing. And so when we click on the prepare tab, we can see down the bottom here, we have different tabs for different design features. They'll be called slightly different things, but in general, they get grouped with the same type of material parameters. All right, so first one is quality, and we've got the layer height. It's a layer by layer process. So you can imagine that the smaller your layer height, the more resolution it's going to be. We talk about this thing called a staircase effect, where if you try and print a curved surface, the bigger the layer height, the more pronounced those steps are going to be. If you think about like a pyramid, then if you want to get less pronounced steps, you need to decrease the layer height. But I'll just leave it at 0.2 for now. Also worth pointing out that there is lots more settings that we could play with down the bottom, but just for demonstration purposes, no need to go through them. We'll always have a strength tab. This is about the structural engineering of it. We can see that we can specify the number of wall loops. Right, this is the number of loops. This is the number of layers and of external walls. And if I just quickly show this to you, let me just go down here like here. So if we have a look, you can see what I'm talking about. We can see that there were two walls. Here's this orange is the first wall, the yellow is the second wall, and then we have something called infill. And the infill is what gives the part strength. So if you want to pick a particular infill pattern, and the pattern is going to have all kinds of different strength cases depending on the load paths, right? So you can see here that I've just got this one because it looks nice and pretty. But you know, we could also have a line pattern, right? Depending on whether it's, you know, in plane stresses, out of plane stresses, you would pick an appropriate pattern to give it that internal strength, right? So the external walls give some strength, the internal pattern gives some strength. So we would be able to pick those features there. Then we will have a support tab. Now, support tab is these green lines. And so we can see here that with the support tab, as we're going up, you know, we can see the different layers, how they're all adding up. But we can see here that there's actually no supports for this first one. Can everyone see that? This horizontal shape has no supports. And you're probably thinking to yourself, well, hang on, didn't you say that gravity matters and that if there's no supports, it's actually going to collapse down? And that is true, particularly for metals, but for plastics, we can actually do something called bridging. And bridging is where, with the viscosity of the plastic and the rate of cooling and the distance that it needs to bridge, then there's no need for supports. It can actually print that. There will be a little bit of sag, all right? That's just part of the realities of gravity. But we can actually bridge small distances without needing to provide supports. But as we get to the top here, we can actually see that there are supports for this cross section here, for this section here. And that's because it's just not possible to print this properly without having those supports. All right, so what were the key things? We had layers, we had strength, whether it was the number of walls or, as we can see, these red bits, the internal patterns. And we also have the supports to support material that is going to collapse under the realities of gravity if it wasn't there otherwise. But once that's done, we're able to preview it. We can have a look at all the different layers. All right. And then once this is done, all we need to do is then print it. Now, I'm obviously simplifying this a little bit, and normally we'd spend 30 minutes talking a bit more about this. But really, once you're ready, all we go is to print plate and away we go. So if I can show that to you, I've already got it loaded up, but let me just start this up so we can see what it looks like. And I'll just talk you through the process, and then I'm happy to take some questions. I can stay on a little bit longer, although I note that our time is almost up. So we can see here the system's just getting ready. There's always a calibration or startup phase for the machine where it needs to get the where it will need to get the bed to a particular heat. It'll also need to get the nozzle to a particular heat so that the printing can be oh, sorry, thank you very much. So here we can see the printer. And so there's going to be a little bit of a calibration during the setup as the machine needs to get ready. And I think you can probably hear it, but it hasn't started. Oh no, we can see a little bit of material coming through. So we can see the material is starting to feed through now. Just takes a little time to get the system up to the necessary temperatures. So the heat bed heats up to around about 60 degrees C, and the nozzle will go up to, so the heat chamber itself will go up to about 220 to get that plastic molten. It's important when we're using the plastic that the heat chamber doesn't go too high. So you can actually see it flushing the chamber. So it flushes the chamber to make sure that the plastic is flowing correctly. So it has the right flow settings. Otherwise, it won't print properly. So I'm just working this with one hand, so bear with me. I'll zoom in once it starts doing something interesting. So if you actually put the heat chamber too high, you can actually burn the plastic and cause all kinds of problems where you have burnt residue inside the heat chamber, inside the actual filament reservoir. But this calibration process is quite important. It takes a couple of minutes to run through. It's also going to do a bed leveling. As you can imagine, if we're doing a layer by layer construction, then how level the bed is, which is where the part's going to be built, is going to dramatically affect the accuracy, and it's going to affect the quality of the part. So you can hear it essentially just running through its own system checks right now. So while we're waiting for it to start its process, was there any questions? I'm going to open up the floor to questions now. So it's just doing some nozzle cleaning and some further bed leveling.
Hey, Daniel, you have a question in chat.
Do I? It hasn't popped up for me. Let me have a look. Ah, cool. Thank you very much, Sky. What type of material? So today we're printing with PLA. This is because PLA is all good for most modeling requirements. When it comes to needing to do more engineering applications, you'd be looking at other types of things like what is it? I'm just trying to. So you could look at PEEK, which is a high ABS or PEEK. These are engineering plastics, so they've got much higher strengths and strain, as well as temperature conditions or material properties. But PLA, this tends to be the workhorse for hobbyists if you just need to be creating visualization or form models.
So if we have questions, did you want us to unmute?
Oh, you can unmute, absolutely.
Okay. So I noticed earlier that when you were going through the slicing program, that there was that section that had no supports. What kind of settings would you be implementing into your program, I guess, or your settings side to allow for as clean of a bridge across a gap like that? Because one of the things that I've found when I do, I have a printer as a hobby, is that any sort of bridging I do, the sagging is excessive or it doesn't cool fast enough for it to complete the bridge.
Okay, yeah, no, great question. So if you are looking at bridging, the usual thing I would recommend, perhaps you've already done this, is to do a bridging calibration test. So the great thing, particularly if you're looking to get into some hobby level 3D printing, just to sort of wrap your head around what is and isn't possible, it's a fantastic way to do it, is you will often want to dial your printer in for all the specific quirks it has in terms of the temperature that it's printing at, but also what its capabilities are. And two capabilities for plastic printing is of interest. The first is bridging, which is what Sky is talking about. And the second one is overhangs. And what angle can you overhang before you need to have supports? So I have no angles in this one. They're all at 90 degrees. But you can have what are called calibration tests. And if I can just pull up a calibration test to show you, you can then use these to dial in and work out what are the limits of your printer. Let me just move this a little bit closer so you can see the action. Okay. All right. Just pull up this image. Sorry, I'll answer your question, Scott. Just give me 1 second. Okay, cool.
That's all right. I just threw in the chat for everybody that was curious, an overhang type of a test where you would run a print and see where your print starts having failure at what angle.
That's exactly right. So a calibration bridging test. Just gonna try and find the first one. Oh yeah, that'll do. So I'm assuming, Sky, you've run a bridging test? You get a bit of a feel?
Well, so with my printer, I've kind of been exploring a lot of the capabilities just by testing different prints, go online, find a print and test it and see how it prints. And so what I've been exploring is, bed adhesion by changing the nozzle temperature and the bed temperature. Because when I first started, I was getting a lot of prints where the base plate was large and the filament was stretching too thin and not having a solid first layer for adhesion. or I
Yeah.
was getting bubbling or curling of the filament. So I was working through uh, those kind of things first, and now I'm getting to the point where it's, angle of overhang and
Yeah,
bridging,
excellent.
the a little bit more advanced stuff in the still beginner level.
Oh no, look, absolutely, and that's the best way to do it, right? Is to just keep doing different prints. That's what I did, as I wanted to wrap my head around what was and wasn't possible. And there's a lot that you can learn and take away from even just running a bunch of hobby prints. Well, the big difference between hobby prints and industrial level prints is size of the build volume, the type of material that they use. But otherwise, a lot of the design principles and philosophies and lessons are directly transferable. So that's really great to hear. Yeah, Sky, yeah. In fact, I believe I have that exact overhang test. So for those of you that are wondering what an overhang test looks like, just in the chat, Sky has posted a overhang test. And so the way they work is you just print those and then you do a visual inspection to see how your printer performed. Each printer will be different and will have different capabilities. And then once you've done these calibration tests, you essentially feed this into your printer profile. And that way, when your slicer is pulling the part together, it knows that for overhangs up to this particular degree, based on your calibration test, no supports are required. So it's just a way of fine-tuning and optimizing your profile.
Maybe I just missed it because I was looking for a bridging test example. But so if you find that you run your test and your prints are causing issues, whether it's the overhang or the bridging, what type of settings would you be altering to improve those? The speed at which it's printing, or
Yeah,
the
so yeah, you could alter the traversal speed. You could also alter the temperature that the material is coming out at, or you could alter your design. So eventually, at some point, reality will force you to conform, right? So there will be some limit where you can't print beyond the overhang requirement. Could be changing the nozzle diameter could also assist, but it sounds like what you're doing is about right. If really the only thing you can play with is the speed that you're moving, the flow rate, the temperature. And once you hit a certain point, you just won't be able to do that. And in
okay,
general, all overhangs will have some sag. It's just whether or not it's A, noticeable, and B, detrimental to the function of the actual component.
okay, and so then there wouldn't be things within the slicing program that it could automatically make assumptions to help correct that necessarily. It would be you applying a slower rate of movement and a faster rate of feed or something like that on a given layer for those bridges.
Yeah, that's right.
Okay.
And you can do a bit of a deep dive into some of the forums. I'm sure that there are people who make it their passion to see how far they can overhang, or how far they can do a bridge before needing to put a support in, for sure.
Yeah, I was just finding that with a lot of my prints, when there's something that's round, um, my slicing program was trying to assume that there was necessary supports in those areas
Yeah.
when you know, the angle of overhang was too much, it would automatically apply supports. And then when you have the supports added into a spherical shape, you know, it takes away from the accuracy of the print, because where they interact isn't
Yeah.
always the cleanest.
Yeah, that sounds about right. And the other thing to note is bridging is best performed on straight lines. You can't bridge a curve because there needs to be something to actually allow it to make that turn in midair. There's no resistance. So lots of interesting quirks when you try and take advantage of that additive manufacturing layer by layer process. Was there any other questions about what we've gone through today? I hope it's been informative, and apologies for all the technical issues. I'm not too sure what happened. I've run a number of webinars over the years, and that's my first time that has been that painful. If you did have any other questions, please feel free to come off mute and ask your question, or you can put it in the chat. And of course, the other thing is, if you remember a question afterwards, please feel free to email me. It'd be more than I'd be more than happy to answer some as well after the webinar has concluded.
Is your email listed in the meeting invite, or did you drop it in the chat that I didn't see?
So it should be in the meeting invite, but also in the thank you email. I will also list my email address as well.
Okay, sounds good. Thank you.
No worries at all.
I've got a question coming in there.
Yes, I can see that. Thank you very much. Just so also just have a nice little view here, so we can see that the part's approximately there, right? So we can see that it's very matching up with what we expected to see from the slicer. No worries at all, Mike. It was my pleasure. So great question, Garland. I'm just posting up the on the screen here. Here is a QR code if you would like to quickly jump to the web page, which has the course information. In terms of where do we offer the 3-day class, we do have public course offerings that we sometimes do, usually around conferences or trade shows. If we get enough interest, we run a public one. Otherwise, we typically come to organizations to deliver the 3-day course. And you can always request a quote through our website or email us directly. But yes, we come with everything. So I'll come with a printer. I'll come with all of the material and the training materials, so that you're able to experience that hands-on workshop within your organization. Of course, if you can swing it, you're also welcome to request a on-site class in Australia if you wanted to make the travel across the ditch. Okay. That's always the problem, isn't it? It's always trying to get the boss to sign off on it. But you never know. Sometimes all you got to do is ask. Was there any other questions? I probably have time for 1 or 2 more questions about additive manufacturing. We can see how the presentation is going over here so far. No worries at all, Garland. You have a great day. Nitish, I can see you've got a question. Feel free to go through.
Thank you, Daniel, for the nice presentation. It was
You're welcome.
great and informative. And I would like to know, is course online or in person? Because right now I'm in Italy, so is it possible to get the course online, or I have to come to Sydney or EIT?
So we do the online courses, and we do a lot of online courses. Specifically for the additive manufacturing, we can do the one-day course online, the additive manufacturing fundamentals. But we're more than happy to come to Italy. We travel and deliver our courses worldwide. We've delivered courses to the US, to the Middle East, to Europe, all around the world. So if you would like us to deliver a course, then all you'd need to do is put through a request for quote, and we would be able to look at that and see. We typically just have some minimum numbers required within your organization for us to come across to Italy, or to any to deliver any on-site course. We just have some minimum viable numbers. But if you send through the quote, we can then have a chat about what that might look like. Does that help, Nitish?
Yeah, thank you very much. I
No
will
worries
write
at
you on email.
Yes, please. Thank you very much.
Thank you. Thank you so much.
Okay, I probably have time for one more question. I can see we're slowly coming down in terms of number of people left. All right. Well, if there's no more questions, I might call it there. So please feel free to reach out. We would love to hear from you if you've got any questions about additive manufacturing in defense, or if you would like to learn more about the courses that we offer. It's been an absolute pleasure. Thank you very much for your patience as we went through those technical difficulties, but I hope you very much enjoyed it, and I look forward to hearing from you soon. Have a great rest of your day.